So two types of residential blower motors. Again, we're focusing on residential, the PSC motor and the ECM. I'm sure you're all familiar with that because that's a long ago change, but they still have to deal with existing equipment in the field. The ECM motor adjusts itself to keep the programmed airflow. And we'll show about the power consumption, although somebody pointed out, I think he's still in the room, that I got to look at volts or watts and amps yes. So that I didn't take care of that in this, wasn't that quick with it. But the static pressure in an ECM system really doesn't tell you a lot about airflow because it's a programmed airflow. And actually a manufacturer did produce an airflow chart. I'm not sure why, but I'll show you it for an ECM system. So this is actually taken in the field. You can kind of see the galvanized behind it. But let's say, again, we got to pick the right type of equipment and the right configuration because electric heaters could cause a little bit more static resistance. So we got to match the way they did it in the lab. So in the field, we find we matched up with electric heaters running at low speed at 208 volts because that will affect things also. And we see a reading of 1/2 inch of water column on the manometer when we put the static pressure tips in to measure, and this would be the total external static pressure. The readings here are laid out a little differently, CFM, watts, and RPM. So CFM is 986, watts are 189, and RPM is 741. The interesting thing to notice here is, as you go across and you range from 0.9 to 1.0 inches of water column, a full range of 0.8, the variation is almost nothing. It's 7 CFM. So this is an ECM motor. So standardized tables or charts should be avoided. From what I can see, looking at just handfuls of them, they are not the same. I've seen people try to use standardized tables. I don't think it's a good idea because already you can see that measurement technique is a little fuzzy depending upon how you do it. And now you're going to add in just this average thing going on. Not a good idea. We do have some resources like a video lesson on our YouTube channel, as well as a download if you're more of a paper learner or you want to see it laid out in diagrams and charts. Those are free. We have a recent addition by my videographer here, Brian Orr, for the HVACR school. He did a video for us doing a pitot 5-tube test with the 510i manometer at his own residence. So take a look at that, and he talks it through very nicely to describe how to set these up and what he's looking for and how to take the measurement. Vane anemometers, we talked a little bit about those. Roger had mentioned the propeller rotates proportional to the speed of air, so it's not about density. There's no need for density correction. And they average over a large area, like 4 inches in diameter, or I call it a large small area. It's larger than a pitot tube. It's larger than a hot wire. I think it's about 1/2 inch diameter for the mini vane that it's averaging over. So it's accommodating more information to give you a better average number more quickly. And they're minimally invasive. They've designed the profiles very carefully. And there's other manufacturers that make these, although the mini vane, I'm not sure no one makes one of those besides Testo. That's unique.
When you compare it to a hot wire, the hot wire is more accurate. It has higher sensitivity.
Yes, absolutely higher sensitivity to changes in airflow. Yep. However, with the mechanical system that these require, they need enough flow pressure to be able to get them to turn, to make the vanes turn, enough wind. And turbulence can affect them in things like a factor called swirl in some outlets, or even off of some motors, you can get swirl. And Bob's nodding his head here, he studied that. That can actually artificially change the way a rotating vane, or even pressure or thermal anemometers work. by creating swirl in the fluid, in the airflow. So again, this sort of gets into real levels of detail, but if you're wondering why all these things don't agree, there's factors for it. Being off in angularity, most of these are pretty good. You can be off about 10% in the angle and get about a 1% error. They've been designed very carefully. If you look at the head on this, it's very smooth, very slick, very aerodynamic. The friction is minimal on these propellers. Even that large vane, if it's passing around, sometimes you could just hold it up in the table and it'll pick up the airflow from those diffusers in the ceiling. I mean, it's that sensitive that it can pick it up. So, I mean, the manufacturers are trying very hard to give you the best possible quality. For the large vanes, supplies and returns, obviously that doesn't work well in a duct, especially in flex duct systems in order to get that return airflow where it's hard to make any kind of in-duct measurement. And the mini vane, it's best in hard duct systems to take in-duct measurements. Not so good on supplies and returns, again, because of those vena contracta and the airflows, the air squirts out of the vanes. One question, like how do I calculate an open area when I don't know it? It's not available. And this was a suggestion given to me by a TSI engineer. He creates what he calls a stub box. Basically, it's field fabricated. They work really good on floor registers, but they don't work so great in wall or ceiling registers because you need to tape them up. But if you place a box around and sweep across the top area, that's a free area, okay? So beneath it, even though there's an open area factor here, which you don't know, if you allow it to convert, you basically create like a capture hood, your own sort of field capture hood, and you can use a traverse device to get it. So a lot of people are trying to be creative out there, you know, kind of skin this beast of measuring airflow. You got to be careful about back pressure, proper dimensions of the box, and challenging when used beyond floor registers. You know, toe kicks, things like that, be very difficult to take this kind of measurement. I didn't pull it out here, but have you all seen one of these? Yeah, a lot of people not. It's like, I heard from the manufacturer that I think they sold 125,000 in 2.5 years. I think that's like every technician's got two, that kind of thing. $50 is the price on this, and as Rick was mentioning, they do have some details in here. This is an old screenshot. I hope they improve some of this because we're not usually talking about MSDS for free area and free space. So there's some oddities to this. I took this screenshot in the original application. This pressure matching method for the Duct Blaster, basically similar to the TrueFlow grid. You take a system operating pressure with everything buttoned up. You remove the access door for the distribution fan, hook up your Duct Blaster. And the Duct Blasters and blower doors are they're pressure making devices, pressure creating devices with a sensor or an instrument built into them. So that's why there's a 2-channel manometer required. They have basically like a pitot array or a pitot ring in them to make the measurement, but there's also a fan to create the pressure. So they create a test pressure and they measure the flow during that test pressure. And you can it's a multi-step process. It's pretty good, pretty accurate, but it takes this kind of construction each time to each site to be very specific. So you need a Duct Blaster and cardboard and tape. I didn't price those out though. Scoops, mini hoods, and flow funnels. You got to be careful about using those outside of their operating conditions. These are designed, I believe it's below 50 at this point, so you can use it for ideally exhaust flow below 50 CFM. That's what they're designed to be used for. There's actually, last couple years, they made a flow straightener, a tube with a grid in it to get rid of that swirl. It's a swirl killer, not a squirrel killer. High efficiency furnaces are squirrel killers. It's a swirl killer, so it deadens that swirl flow so that the device doesn't get impacted by that. So that's an adaptation to that product. But smothering the outlet, the back pressure can cause the system effect and things to talk back. Exhaust fan flow meter, basically it's a flow box. It's a box that has a calibrated door opening in it so that when return air is flowing through it within its range, it creates a negative pressure inside the box. And that pressure, if you know this square, the opening, it's called the open hole formula, you can actually determine what the airflow, the CFM, is. You do need a precision digital manometer to get the Pascal readout, and the measurement range is 10 to 124 CFM on exhaust only or return only. You go out of that and there's too much box pressure and it won't work. It doesn't function. The digital manometers we patched around before have those calculations built into them, or there's actually a sticker on the side of it. If you choose not to use one of their products, you can actually use it with anything that has a good Pascal readout. So you place it over the fan grill, air is drawn through this calibrated opening, and the meter itself tells you the CFM. So this is, we talked about before, this is a bulk measurement on exhaust or returns. So this would be a bulk measurement. One thing, you slap it on, you get a good measure. This is the one where I was laying it on top of a grill, and then when I taped the seal down, I got the change in it. So I learned a lesson. You really have to pay attention to air sealing. Even with the lowest of flows, air sealing is critical. The box pressure goes above or 9 or above, you're in a no man's land where you're no longer getting a CFM calculation from it. The box is pretty cheap, but the manometer itself, you need to get a Pascal range manometer to do that. They're like the $500 to $1,000 range. There's actually some good instructions from a consultant, Joe Midash, who created this on how to hook up both of the meters. It's hard to see in this slide here, but it'll tell you when you get above 8 Pascal, and it will also tell you the flow range from those 2 meters directly. So the setup steps are there. Capture devices, capture hoods, I do want to cover this. We were running a little bit late on time, but these are important because, as you heard before, these are the ones that are recommended. There are different ranges, 500 to 2,500 CFM. Perhaps someone will invent one that's 1,000 CFM that's more designed for residential applications. 2 manufacturers in the room. Some of the limitations are mass-dependent airflow, but again, a lot of them have built into them either through the meter or through actual sensors embedded in the device to give you those corrections for air density. So the bag inflation is cheap, but the flow hoods are in the $1,500 to $3,200 range. You can't really see it here at all, darn it, but there's a grid that's built into the skirt of the Testo 420. So this going with the flow, the idea here is it's a swirl killer, it's a diffuser to make more laminar flow to put against the flow sensor at the base of the unit. So that's a very clever, unique design upgrade. The Dwyer Smart Air Hood, again, addresses some of these going with the flow, understanding fluid dynamics. I think I stole one of his slides from his presentation, but they did a lot of study with fluid dynamic, computational fluid dynamics, a lot of equations, a lot of engineering work, looking at how traditional flow hoods get recirculations and chokes and eddies in there. And they created one, it looks kind of like a shower head, but basically the flow just kind of slips through 4 flow sensors. It's got quad sensors in it, which are pitot arrays that allow you to take instead of diverting it all to one, this lets it flow through 4. So it's going with the flow of the air. I'm going to skip over the bag inflation device. But the only thing I want to talk about here is just that 3 to 20 seconds where it comes from, how rapidly things change if you're trying to use a stopwatch. So you can have a change of between almost 200 and 150 or 50 CFM using that bag within a quarter of a second. So if you're using a bag inflation device, pick a bag big enough for your airflow so you're in this transition range. We're starting to level out and you can get a linear number, and it isn't as big a change if you're a little bit off with the stopwatch, if you care to try that. You may even want to try that with a smaller bag, again, an educational setting with students, and say, how quick can you time this? How quickly does the CFM in this bag fill up? The air probe is an amplified averaging pitot tube. Those are also passed around. They had multiple points, multiple holes in them. These are designed to be sensors to put in variable air volume system to go back through a control system to feedback airflow in a branch run. They must be the exact size of the duct. You can't use one that fits. It can't be sticking out. It can't be too short. It has to go across the full duct to get the correct measurement from it. You need a precise manometer to get the low end readings on its scale. And you must use a specific equation. I'll show you that equation here. This looks like, hey, great, it's linear, but it's actually logarithmic. Go ahead.
With those tubes, you got to make sure you have so much liquid duct before and after that. So you gotta
Absolutely. Yeah. Didn't mention it here, but you're absolutely right. You can't have turbulent flow because you're going to get those dead zones, et cetera. I did a quick calculation here. If you had like 800 CFM over a 1 square foot area, you'd be in the 1/10 of an inch of water column range, which is sort of like the sweet spot of operating for a lot of pressure sensors. But if you get down to lower velocities, you're going to get to much lower pressures, and it's going to be hard to extract information from these. Dwyer has what's called a plastic airflow sensor, similar type of concept, the averaging pitot tube. Must use the manufacturer's specific equation, which is an adaptation of that pitot tube equation. But one of the big factors here is, they even state it, you might need to calibrate it before you can use it in the duct you're using it in. Again, it's not meant to be a measuring device. It's meant to be calibrated to be a measuring device. Yes?
Do you buy the extenders or do you need to buy it?
No, they're pre-assembled. Yeah, I'm not sure how they're welded together, but they're pre-assembled. But be careful using this as a measurement tool. It's meant to be something designed into a system, checked, calibrated, and then used. And people are sometimes attracted by the price point and feel like that's a way of making a measurement. And it's really not a good measurement, but I need to talk about it. This is a bad gateway drug. I don't have time to show the comparison spreadsheet, but here's an illustration of the powered flow hood. We talked about it before. Basically a fan with a measurement grid, a manometer that will tell you the pressure under the hood. So the fan can run at the right speed to give you 0 pressure under the hood. So it looks like the room pressure. There's no delta P between the hood and the room. Unfortunately, no longer in production, but some people have them. This powered flow hood made in Norway has a sensor in the fan to correct. It runs up to 500 CFM. We call it the ultimate in measurement. It's single piece, battery operated. You literally turn it on, seal it over the grill, press a button, and in 15 seconds, your CFM number is there along with the direction of flow. Because it's invisible to the grid, to the grill, you could actually take paintball measurements with it because it's going to intercept what the airflow is. You know, theoretically, you could take paintball measurements and intercept one part of a grill, another part, because the opening on it only goes up to, I think it's 16 by 16. But it does have this ECM fan motor. If you're directly on the fan, like an exhaust fan, it does have that feedback interference thing where it's trying to ramp up and the fan's trying to compensate, and they go back and forth, and the number ends up being too high because the fan scales up to account for the restriction. Are there any questions at this point? Yes.
For my students, and I guess a lot of technicians out there, they can't just go buy all of these tools.
Right.
If, you know, for the students just graduating and they're going to go buy one airflow measuring tool, what would you tell them to go buy?
What are they trying to measure? System airflow?
That's part of what I'm getting at is,
Yeah.
you know, which one is going to be most versatile, easiest to use for the beginning student or beginning tech.
Well, again, it depends on what their application is. Are they trying to set up the airflow in a residential air conditioning or heating system? Yeah, I would say teach them how to do the static pressure method. I think the heat rise method is too error prone. I think the static pressure one is going to be easier to use. But again, go through the nuances of this. If you give me your card, I'll email you these slides. So if you'd like to teach off of these or ask me a question about them. And if they were trying to measure like supplies or returns, a lot of times you can use a technique called proportional balancing. Just set the blower speed and try to get the proportionate air right in the room. You could use that small $50 device to get you there, get you close. And again, you don't always need to take a precision airflow measurement. Sometimes you just need to be in the ballpark. So that's why we talk about them all. Any other questions? Make sure you sign the sign-in sheet to get your CEUs. Thanks. You're welcome. Thanks. You're doubly smart. Thank you. You're welcome.